Hi, Year 12. This is our last lesson for the topic of statistical analysis for Extension 1 Mathematics. In this lesson, we're going to learn about sample proportions. So this is what we've covered so far. We learnt about Bernoulli random variables and Bernoulli trials. Then we looked at binomial distribution, including the mean and the variance, and binomial probabilities. And last lesson, we learnt about normal approximation of a binomial distribution. So let's start with population proportion. If a population has members that share a particular characteristic, we can calculate the population proportion, P. This is a Bernoulli variable because you either have the characteristic or you don't. Here's an example. In a population of 20,000 people, 6,307 have blue eyes. The population proportion is 6,307 divided by 20,000. Now here's the thing. Very often we don't know the true value of P as we cannot survey the entire population. So this is what we can do. If the population is large, we can use a sample proportion to estimate the proportion of a population that share a particular characteristic. And here's the notation for sample proportion. We call it P hat. And P hat is equal to X over N. X is the number of people who have the characteristic. N is the number of people in the sample. Now obviously you would take different samples and it's going to vary the number of people in each sample who have the characteristic. Therefore P hat is a random variable and it's going to have mean and variance. So let's work this out. The expected value of P hat, well that's the same as the expected value of X over N. And I can split this up. X is a variable, N is not. Now what's this, E of X? Well, X is the number of people in the sample who have this characteristic. That's a binomial distribution. And the expected value of a binomial is NP, so number of trials times the probability of success. So our expected value of P hat is actually equal to P. And the variance? Well, the variance of P hat is also equal to the variance of X over N. Now, instead of going to a binomial distribution formula, I'm going to use this formula from our reference sheet, this one in particular, which is the variance of a discrete random variable. So I'm going to rewrite this in terms of this. And I haven't used mu, I've used expected value of X over N. All right, again, I can move these N's out. So have a look at this. Brought that n squared out here, and this n squared's come out here. And I can factorize that 1 on n squared out, and I'll end up with e of x squared, take away e of x all squared, which is actually the variance of x. And we know the variance of a binomial distribution. It is np brackets 1 minus p. Tidying that up, the variance of p hat is p brackets 1 minus p all over n. Now here's the catch. It's not given for you on the reference sheet. You get the expected value and variance of a binomial distribution, not of a sample proportion. So you are going to need to memorize these formulas. Now, in the past HSCs, there's been one question where they gave the formulas, and there's also been a question where they didn't. So my advice is memorize them. I'm going to talk to you briefly about the central limit theorem. It's not part of the syllabus, but it's really important in understanding why we're going to do what we're going to do. If we take a sample from a normal distribution, then the means of the samples will be normally distributed. Okay, make sure that makes sense. I've got a normal distribution, I take loads of different samples, those means are going to be normally distributed. But here's the central limit theorem. Even if the population is not normal, if the sample size is large enough, then the means of the samples will be normally distributed, which is pretty cool. So this is what is called the central limit theorem. The sampling distribution of the mean will always be normally distributed as long as the sample size is large enough. It doesn't matter what population you're drawing your samples from. Now let's have a look at that. So here, the population is normally distributed. Here's a sample size of 1, so we're taking lots and lots of samples, and the sample size is 1. It's pretty normal looking. Here the sample size is 25, but we're expecting that If we're taking samples from a normal distribution, we would expect the means of those samples to be normally distributed. Here we've got a uniform distribution. So sample size of 1 doesn't look normal at all, does it? But sample size of 25 starts to look normal. And here we've got a positively skewed distribution. Sample size of 1 doesn't look normal at all, looks positively skewed. Sample size of 25 is starting to approach a normal distribution. So why am I telling you all this? Well, the central limit theorem works for sample proportions as well. Now, in the previous couple of slides, I've been talking about the distribution of sample means, which is beyond the syllabus. But the distribution of sample proportions, that is in the syllabus. So we can use the central limit theorem, provided n is large enough. And here's the condition. We need 3 standard deviations either side of p to lie wholly in this interval. So what does this mean? It means that the distribution of sample proportions is approximately normal with mean p and variance p multiplied by 1 minus p over n. Here's an example. It is known that 16% of people in a certain town have dyslexia. A sample of 200 people is taken. Find the probability that in this sample less than 10% have dyslexia. Now we can tell that this is a sample proportion question because of this number here. It's not the number of people in the town who have dyslexia, it's the proportion of people. So we're going to use our formulas for sample proportion for mean and standard deviation. So the mean is going to be 16%. And standard deviation is the square root of p multiplied by 1 minus p all over n, which is 0.026. Now we can distribute our sample proportions, or our p-hats, as normal with mean 0.16 and variance 0.026 squared. All right, how do we answer the question? We want less than 10% to have dyslexia in the sample. So probability that p-hat will be less than 0.1. Because we can do a normal distribution, we can use a z-score. So we want z to be less than 0.1, take away the mean divided by the standard deviation, or z is less than negative 2.31. And then we have to go to tables. Now I've done enough questions where I've shown you the tables that I'm not going to do it. I'm just going to pretend that you can do that. And our answer is 0.0104. B, between 15% and 20% have dyslexia. So here's our statement saying that p-hat is normally distributed. Now let's set up our probability statement. We want p-hat to lie between 0.15 and 0.2. And here are our respective z-scores. And again, reading off tables, we get the probability is 0.5862. C, is it valid to use a normal distribution in this case? So we're going to work out 3 standard deviations either side of the mean. So mu take away 3 standard deviations is 0.082. Mu plus 3 standard deviations is 0.238. So yes, since both values lie in that interval 0 to 1, it is valid. Now is this ringing any bells for you? Hopefully it is. What's that 3 standard deviation stuff? Remember the empirical rule where we've got 3 standard deviations either side of the mean? Do you remember what percentage lies here? 99.7%. So we are 99.7% confident that we're within this interval, which is where we want to be, because this proportion, it's a probability. It's in between 0 and 1. If we were outside this interval, we could potentially have a probability that was negative or greater than 100%. Here's a second example. A binomial experiment with 50 Bernoulli trials has been used to estimate the probability of success P. The real value of P is 0.25. Find the probability that the experiment will give an estimate that is within 0.01 of the actual value of P. All right. So we need p-hat then to lie between 0.24 and 0.26. Does that make sense? Now we've got 50 Bernoulli trials here. So remember p hat is equal to x over 50. So we would like x to either be 12 or 13. So out of our 50 Bernoulli trials, we would like 12 successes or 13 successes. So this is what we want, the probability that x lies between 12 and 13, including 12 and 13. Now we could go to z-scores and then to tables to work it out. Perfectly valid method. You could even do a continuity correction if you wanted to. It's actually just as easy and more accurate to use binomial probability because we've only got two values to do. So let's work these out. So we've got 50 C12, probability of success to the power of 12, probability of failure to the power of 38, plus 50 C13, probability of success to the power of 13 multiplied by probability of failure to the power of 37 into the calculator gives us 0.255. I'm going to talk to you briefly about confidence intervals. It's beyond the syllabus, but the more understanding you have of this, the better you are able to interpret the questions. When estimating a statistic, we want some assurance that our estimate is correct. A confidence interval is a range of estimates for an unknown parameter. And the most common confidence interval is 95%, mainly because it is two standard deviations either side of the mean, but we also use 90% and 99%. If we have a confidence interval of 95%, this means 95 times out of 100, the sample will contain the real statistic. Here's an example. I watched 58 games of football and found that 78% of the games were won by the home team. Find the 95% confidence interval of the true proportion of games won by the home team. All right, what does this mean? 95% of the data lies within two standard deviations of the mean. And here we have got a sample proportion which we can normally distribute. So we know that p hat is equal to 0.78. Now normally we would work out the expected value of p hat and we would say that that was equal to p, the true proportion of games. We actually don't know it. So we're going to use 0.78 as an estimate. So mu is 0.78 and sigma is the square root of p hat multiplied by 1 minus p hat divided by 58, which is n. So our standard deviation is 0.054. So we want to work out 0.78 minus two standard deviations and 0.78 plus two standard deviations. So we can say with 95% confidence that the true proportion of games won by the home team lies between 67.2% and 88.8%. Okay, here's a past HSC question. At a certain factory, the proportion of faulty items produced by a machine is P is equal to 3 on 500. Which is considered to be acceptable? To confirm that the machine is working to this standard, a sample of size n is taken and the sample proportion p hat is calculated. It is assumed that p hat is approximately normally distributed with mu is equal to p and sigma squared is equal to p brackets 1 minus p all over n. Production by this machine will be shut down if p hat is greater than or equal to 4 over 500. The sample size is to be chosen so that the chance of shutting down the machine unnecessarily is less than 2.5%. Find the approximate sample size required, giving your answer to the nearest 1,000. So what do we know? We know the true proportion of faulty items, so that's P. We know that P hat is going to be normally distributed. And we know the mean is P, and this is the standard deviation. So we can actually substitute P into these formulas. So mu is going to be 3 on 500, and sigma squared will be 3 on 500 times 497 on 500 divided by n, which is equal to 1,491 divided by 250,000 n. So p hat is normally distributed, mean, and variance. Now this is what we want. We want the probability that any sample proportion being greater than 4 on 500, we want that probability to be less than or equal to 2.5% because that means we're going to shut the machine down. So let's go to a diagram. There's our mean, and here's our top 2.5%, and that cutoff there is 4 on 500. Now let's replicate that over here, 2.5% here. What's this percentage in here? It's 95%, isn't it? So this point here is 2 standard deviations above the mean, which is good because we don't have to go to tables. So we want mean plus 2 standard deviations to equal 4 over 500. All right, let's solve this equation. Take the 3 on 500 over the other side and then divide by 2. Square both sides. Invert both sides. Multiply by 1,491, divide by 250,000. So n is equal to 5,964. So provided the sample size is at least 5,964, then the probability of shutting the machine down unnecessarily is going to be less than or equal to 2.5%. Okay, there are 2 normal approximations that you'll be asked to do. There's the normal approximation of a binomial distribution, that's what we covered in the last video, and you will see a Bernoulli variable, success, failure. Then there's the normal approximation of sample proportions, and in this case you'll see a sample proportion, you may see p hat. So let's have a look at the questions that have been asked so far. So the first one, here we've got a recent census showed 20% of the adults in a city eat out regularly. And we are looking at sample proportions. Can you tell that? The mean and standard deviation of the distribution of sample proportions. You can also see that we don't need the formulas because we've been given the mean and the standard deviation, and you're also given z-scores. And we've got this one. In this case, we have got a normal approximation to the binomial distribution. Okay, so not sample proportions. About this one here, this is the question that we just did, and we can see that we're given formulas for the sample proportion. And finally this one, what have we got here? We have got not a lot of information in this question. Probability of 5%, passenger books a flight and misses it. So that kind of makes you think that it's a sample proportion, but at no point in this question are they taking samples. So this one is a binomial distribution that we're going to approximate as a normal distribution. Okay, that's actually it for statistical analysis for Extension 1 Mathematics.